now that we've covered the theory behind orbits and gravity, we can move on to looking at the specific orbits of the planets, moons, and other things within the solar system. So let's start with the inner planets, the planets from Mars on in, or from Mercury out to Mars, however you like to see it. That includes Mercury. I know the print is a little bit small here. This is Mercury's orbit, Venus, Earth, Mars, and it's color-coded in a nice sort of way. So there are green dots and red dots. The green dots refer to a location called the perihelion of the orbit, the closest approach to the sun, and the red dots are the aphelion, the furthest distance from the sun. So for each planet, there is a perihelion and an aphelion. Perihelion, aphelion for each one. And that's because their orbits are not circular, they're ellipses, and so at some point they're going to be closer and some point they're going to be farther away. The other color coding here refers to when the object is in the ecliptic plane or above the ecliptic plane and below the ecliptic plane. It's a little bit less important for what we're talking about here, but I'll describe it because the ecliptic is an important idea. So remember that the ecliptic line is defined by the path of the sun in the sky. So if you're standing here on Earth and you're looking out at the sun, as the Earth moves, the sun is in a different direction relative to us. So here we are on Earth, we look at the sun, we would project it out this way. When we're over here in Earth's orbit, looking at the sun, we would project it off this way. And so the zodiac constellations are the constellations that would be out on this perimeter that are in line with the Earth and the sun at some point during the year. And so what we've been talking about is the ecliptic line really defines a two-dimensional plane in space. And so Earth's orbit is within that plane. So that plane is defined by the Earth and the sun. And so everything in that plane of space is in the ecliptic plane. Well, so what the diagram is showing us is that the planets are not always in the ecliptic plane. Their orbits are kind of tilted a little bit. If you looked at this from the side view, they would not all be in line with one another. They're sort of slightly different angles going around the sun. So taking a look here at Mars, Mars is above the ecliptic plane, then it intersects with it and goes below the ecliptic plane. The other thing I want to point out here is that Kepler figured out that these orbits were ellipses, not circles, but he didn't have access to a picture like this. He did this from the observational data. So his data was precise enough to tell that Mars' location here at its aphelion was farther away than its location here at the perihelion, all from looking at Mars as a dot of light in the sky and being able to determine how far away it is at that moment in time. So when you think about that he figured all of this out, that these planets were not perfectly circular orbits, it's pretty impressive, right? Just take a look at Mars' orbit and put your hand over the circles in the center. And you could probably imagine that orbit is just a circle. But when you remove your hand and you can see the location of the sun, I think it's reasonably clear that the sun is not exactly in the center, right? So from our view on this, it's not too hard to see that the orbits are not perfectly circular. Not Newton. Kepler did this just by looking at observational data of the dots of light as viewed from Tycho Brahe's chair in his observation room. Onto the outer planets. So the outer planets, we have Jupiter, Saturn, Uranus, Neptune. All of the other planets would be located in here, within that orbit. Now, similarly, they have a perihelion and an aphelion. Each one has a perihelion and an aphelion, and they are not all in the ecliptic plane, right? They have times when they're above and times when they're below the ecliptic plane. And so in that way, they're similar. Their orbits are all fairly circular, but still elliptical, with the sun at one focus. But I should mention that Uranus and Neptune were not known at the time of Newton. So everything that they had done up to that point was in thinking about the planets out to Saturn, because those planets would all have been really easy to see in the night sky. They're reasonably bright. Even for novice astronomers, when you go out to look at the sky and one of the planets, Mercury, Venus, Mars, Jupiter, Saturn, if one of those planets is out, you can find it. It's pretty bright. It'll be one of the brightest things in the sky. That's not true for Uranus and Neptune. Uranus was not found until it was by accident through a telescope in 1781, and Neptune wasn't found until a couple of astronomers realized that the orbit of Uranus was a little bit irregular. It wasn't exactly following Newton's laws. Or it was following Newton's laws, but it wasn't following the laws as if it was only being pulled on by the sun. There had to be something else tugging on it to make its orbit a little bit irregular. And so they predicted that there has to be some other planet out there, and they predicted about where it would have to be. And soon after that, it was discovered in about that location in 1846. So we've known about Uranus and Neptune only for the last couple hundred years. And those are telescope objects. Those are not things that you're going to find looking out with your naked eye. And probably not with binoculars either. You'll need a real telescope to find those two planets. But one thing you can definitely find with telescope, is the planet Jupiter and the 4 Galilean moons. And so those are depicted here. I mentioned them in the previous video, that we can use the theory of orbits and gravity by Kepler and Newton to describe the motions of moons as well as planets. And so we're going to do that with the Weighing Jupiter lab this week. So what you'll do is you'll open this view in Stellarium, and there's an instructional video showing you how to do this. And you'll track the motions of the moons around Jupiter, and use that to measure the mass of the planet Jupiter. Okay, so what we've been talking about applies equally well to our moon, to the moons of Jupiter, to the moons of Saturn, to the moons of any planet, to any asteroid, any comet. It's a completely general theory about how orbits and gravity works. So here's a little look at some of the other things that are in the solar system. There are namely asteroids and comets out there in addition to the planets and moons. And one of the more famous of these, perhaps the most famous, I think, is Halley's Comet. So hopefully some of you have heard, or maybe most of you have heard of Halley's Comet. It comes to see us every 75 years, and it's been doing that for a long time. The first person to have observed it and recorded it was Edmund Halley, who was a contemporary of Isaac Newton. And every 75 years since then, we've seen Halley's Comet, and there's historical records of it. The next time it'll come back around is the year 2062. And so bookmark that on your calendars. 2062, we'll take a look at Halley's Comet. Now, we only get a short look at it because of essentially Kepler's second law, that things are moving fast when they pass near the sun and then slow when they are farther away from the sun. So Halley's Comet takes a 75-year orbit, but it spends most of its time out far, far from the sun in a very short time in close where we can see it. The diagram's a little bit confusing. Halley's Comet's orbit is actually this one. So it passes in here, kind of intersecting with Venus's orbit. It might pass this close to the Earth. I don't know where Earth will be along its trajectory. It could be we're very unlucky and the Earth is over here when Halley's Comet comes through, and maybe we won't get a great look at it. Or maybe we're really lucky and we're right here when Halley's Comet comes through, or right near here and it'll pass right by. That's sort of luck of the draw. But in 2062, Halley's Comet should come back through, and we should get a good look at it. Well, hopefully. All right, so we've talked about the things in the solar system that are in orbits as a result of the formation of the solar system. But we've also taken advantage of this for our own purposes, and primarily we've used this for telecommunications by putting satellites up into space. And so the same laws that apply to all of these other things also apply to the satellites that we put into space. Essentially, we're doing now Newton's little experiment, except we're not throwing a rock off of a mountain. We're blasting a satellite into space and giving it a push and putting it into this perpetual free fall, this orbital motion. And since 1957, we've been putting things into space, and now there are thousands of satellites that are in Earth's orbit. One of the most interesting satellites is the International Space Station. That's what's pictured down here. It orbits the Earth every 90 minutes, and you can see it occasionally. When you do, it's very bright. It's the third brightest object in the sky, I believe, behind the Moon and Venus. And so if you go to there's a link here. If you go to the website, it can show you the current path that the ISS is on, and if it's happening to come through overhead where you can see it. So it depends on the trajectory, and so it's not like I don't know right now if the ISS is visible, but periodically it does become visible, and you can see it gliding through the sky, and it's really, really bright. So we've put lots of satellites into orbit, but we've also sent a lot of things into the solar system to go explore the objects that are out there. And there's been lots of missions. I just wanted to mention two. The first solar system exploration mission was called the Voyager mission. Started in the 1970s, was launched in 1977, and continued for the next decade plus into 1989. And there was two sent, Voyager 1 and 2, and they were sent on paths to kind of intersect with all of the outer planets. So they swung by Jupiter, they swung by Saturn, and then one of them took a trajectory off to pass by Uranus and Neptune, and the other got kind of shot out of the solar system. So the pictures that I saw as a kid in my book of the planets largely came from this Voyager mission. Those were the closest approach to these outer planets, and so they're the best look that we had at them. More recently, we have the New Horizons mission, and this was the mission to go out to Pluto. You'll notice that Voyager didn't make it to Pluto. So this is a very complicated calculation to get this satellite to intersect with all of these different things and then head out. It was too much to also intersect with Pluto for this mission. So we sent a special mission out launching in 2006 that eventually made it out to Pluto in 2015. So waited a long time to get a good look at Pluto. And so I wonder, do you know what Pluto looks like? Certainly when I was a kid growing up in grade school seeing pictures of planets, there was no pictures of Pluto. at least not any very good ones. And so I wonder if any of you have seen a good picture of Pluto. If you haven't, it's one of my favorite pictures in all of astronomy. This is what Pluto looks like. So we had never gotten this view. Our best telescopes, Pluto's just too small and too far away to get a high-resolution picture without actually going there. The New Horizons mission went out there and took this picture of Pluto, and it's really just fantastic. The most notable feature is this right here. It's essentially like a big white heart, and so that's what people describe, is that Pluto has a big white heart on it. And then you see all sorts of different kinds of terrain and craters and different ice formations. So it's a much more interesting object than we could have even have imagined. And this came by our understanding of orbits and gravity, knowing how to send something to guide it to space in order to swing by Pluto and take some nice pictures on the way out. All right, last thing, we've put a lot of things into Earth's orbit, sent a lot of things out into space. This isn't drawn to scale, so the dots here are not to scale size of the satellites, but it does give you a sense of how much stuff is out there, and that it's spread all over in near and farther Earth orbit around us. So we've taken advantage of the law of gravity and understanding how orbits work to a tremendous degree in order to explore, to learn about things in space, to do science experiments that couldn't be done on Earth, but then also in everyday life, telecommunications, sending signals back and forth to different points on the Earth. It's become incredibly valuable, and it's actually essential to life as we know it. All right, so I think that's it for tour of orbits in the solar system. Next week, we're going to come back to Earth a little bit and think about the Earth-Moon interaction and the Moon's orbit in a lot more detail, and how it has influences on our timekeeping and our phenomenon that we can observe here on the Earth.